We have learned what quantum states are and how to measure them. Now comes the crucial question. How do quantum states change over time? This is where quantum evolution enters the picture. The set of rules governing how quantum systems transform from one moment to the next. Understanding this evolution is the key to building quantum computers that actually compute. At the heart of quantum evolution sits the time-dependent Schrödinger equation, which is the cornerstone of non-relativistic quantum mechanics. Let me break down what this equation tells us. Psi is the wave function, the complete description of our quantum system. H bar is the reduced Planck's constant. H is the Hamiltonian operator. It encodes the total energy of the system. This equation governs everything from atoms to quantum dots to superconducting qubits. In quantum computing, we control evolution using quantum gates, discrete operations that transform quantum states in precise ways. Quantum algorithms are then constructed as sequences of these gates. Think of it like choreography. The Schrödinger equation describes the physics of the motion, while quantum gates are the specific dance steps we design. Here's the problem. Many quantum systems have complicated Hamiltonians made up of multiple parts that don't commute with each other. In mathematical terms, that means given two operators A and B, AB is not equal to BA. This creates a computational nightmare. How do we simulate the evolution of such systems? The solution is called Trotterization, named after the mathematician Trotter. The idea is elegant. If you can't easily compute the evolution of a complex Hamiltonian, H is equals to A plus B all at once, break it into small time steps. For each tiny step, evolve under A, then evolve under B. If your time steps are small enough, this approximation becomes arbitrarily accurate. This is far more practical than using the alternative, the Dyson series, which requires computing an infinite series of nested integrals. Trotterization gives us a way to simulate quantum systems on quantum computers efficiently. It is also how many quantum rhythms like those simulating molecular chemistry actually work in practice. Let's talk about a special type of quantum state called the stationary energy eigenstate. When a quantum system is in a stationary energy eigenstate, something remarkable happens. While the quantum state itself evolves in time, which is acquiring a phase factor, the probability distribution remains constant. Picture a guitar string vibrating its fundamental frequency. The pattern doesn't move along the string. It oscillates in place. Stationary eigenstates are similar. Stationary patterns in a quantum probability. That's the ideal case, a perfectly isolated quantum system. But here's the reality. Quantum systems are never completely closed or isolated. They interact with their environment, leading to decoherence, which is the loss of quantum superposition, dissipation, which is the energy leaking into the environment, and noise, which are random fluctuations disrupting the quantum state. This is why building quantum computers is so challenging, because we are fighting against nature's tendency to disturb our carefully prepared quantum states. When a quantum system evolves in isolation, ignoring the measurement, that evolution is described by unitary transformations. Mathematically, a unitary transformation can be thought of as a rotation in Hilbert space, which is the abstract mathematical space where quantum states live. These transformations preserve the length, of the quantum state vector, maintaining a total probability at 1. This is exactly what quantum gates do. Each gate applies a unitary transformation to quantum states, rotating them in precise, controlled ways. This brings us to the fundamental building block of quantum computing, the qubit. A qubit is a two-level quantum system, the simplest possible quantum system that can store information. It exists as a superposition of two basis states, conventionally labeled Ket0 and Ket1. While classical bits are locked into either 0 or 1, qubits can be in any superposition, alpha 0 plus beta 1, where alpha and beta are complex numbers satisfying alpha squared plus beta squared equal to 1. This two-level structure makes qubits mathematically tractable while still providing the quantum advantages we need for computation. There are two fundamentally different approaches to quantum computing based on how we harness the quantum evolution. One, we have the universal quantum computing, which is gate-based. This is what most people think of as quantum computing. We apply sequences of quantum gates to manipulate qubits, building up complex algorithms step by step. It's like classical computing but with quantum operations. 2. Direct simulation, which can be quantum annealing or adiabatic quantum computation. This approach leverages the natural evolution of quantum states according to the time-dependent Schrödinger equation. Let me explain how this works. Adiabatic quantum computation follows the ground state. Imagine you have a quantum system starting in the ground state, which is the lowest energy state of some initial Hamiltonian. Now, you slowly adiabatically change that Hamiltonian to a target Hamiltonian whose ground state encodes the solution to your problem. Here's the quantum mechanical promise. If you change the Hamiltonian sufficiently slowly and without encountering any energy level crossings, the system will stay in the ground state throughout the entire process. It follows the evolving ground state from start to finish. The probability of the system jumping to other energy states decreases exponentially with how slowly you make the change. Consider a spin qubit in a time-dependent magnetic field. Initial state, which is the Hamiltonian H initial, is Z. The spin is aligned with the magnetic field in the Z direction. The target state, we slowly rotate the magnetic field to the X direction, represented by H target is equals to X, which is a ground state of state plus. We perform this rotation adiabatically slowly enough. The qubit's ground state evolves smoothly from 0 to plus state. The quantum system tracks the ground state throughout the transformation. This is the principle behind quantum annealers, specialized quantum computers designed to find optimum solutions by evolving the ground state of the problem-specific Hamiltonians. Now let's get practical. How do we actually manipulate qubits in real quantum computers? One fundamental phenomenon used in spin 1/2 systems is Larmor precession, also called the spin precession. When a quantum particle with spin is placed in an external magnetic field, the interaction between the particle's magnetic moment and the field causes the spin to precess, to rotate around the direction of the magnetic field like a spinning top wobbling as it spins. On the Bloch sphere, this appears as the quantum states vector rotating around the z-axis. The frequency of this precession is proportional to the strength of the magnetic field. In quantum computing, we exploit this precisely by applying an external magnetic field for a designed time interval. We can rotate the qubit spin by exactly the angle we want. This is how we implement the z-axis rotation gates, like the poly z gate and phase gates. It is elegant in its simplicity. We are just letting physics do what it naturally does, but with precise time. Larmor precession gives us z rotations. But what about the X and Y rotations? Rabi oscillation occur when two-level quantum system is subjected to an oscillating driving field, typically a microwave pulse in a superconducting qubit or a laser in atomic systems. Here's the key. When the frequency of the external driving force matches or is resonant with the energy difference between the two quantum states, something special happens. The probability of finding the system in one state versus the other oscillates periodically with time. One complete cycle where the system goes from 0 to 1 and back is called a Rabi cycle. This gives us exquisite control. By applying a resonant pulse for precisely half a Rabi cycle, we create a perfect superposition. Apply it for a full cycle and we have flipped the qubit from state 0 to state 1. On the Bloch sphere, Rabi oscillations appear as rotations around the X and Y axis, depending on the phase of the driving field. Together, these two phenomena gives us complete control. Larmor precession, Z-axis rotations, Rabi oscillations, X and Y axis rotations. With rotations around all the three axes, we can move a qubit to any point on the Bloch sphere. This is how we implement arbitrary single qubit gates in real quantum computers. Before we conclude, I need to address a common misunderstanding. Many people think quantum mechanics is the Schrödinger equation. It is not. The Schrödinger equation governs non-relativistic quantum systems, systems where particles move much slower than the speed of light, and quantum effects dominate over relativistic effects. But when you venture into the realm of high energies or particles moving near light speed, different equations take over. For fermions, like electrons at high energies, the Dirac equation is used, which naturally incorporates both quantum mechanics and special relativity. This equation even predicted the existence of antimatter. For bosons, like relativistic photons or other spin-zero particles, the Klein-Gordon equation, which describes relativistic scalar particles, takes over. Quantum evolution is how quantum states change over time. In quantum computing, the Schrödinger equation provides the theoretical foundation. Unitary transformation describes the ideal isolated evolution. Quantum gates are the practical tools we use to control that evolution. Larmor precession and Rabi oscillations are the physical phenomena we harness in spin 1/2 systems. Trotterization lets us simulate complex quantum systems. Adiabatic evolution offers an alternative computational paradigm. Understanding these principles is essential because quantum algorithms are ultimately just careful, orchestrated sequences of quantum evolution designed to solve problems that are intractable to classical computers.